Okay, so we're gonna work now on multiplication and division on different bases, and to understand how we can translate this model we just learned and algorithms for our base 10 into any other base. Okay, so let's do 43 in base 5 times 23 in base 5. So remember, first we're going to draw 43, so that's the same we did when we worked in base 5, except that now our longs consist of 5 units, right? So 40 will mean 4 longs, and again the difference is that now, let me try to make it more straight. Now each long has 5 units, so 1, 2, 3, 4, 5, and so on. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so we have 4 longs and 3 units. So we're gonna draw it here. Okay, so now we're gonna first multiply it by 3, right? Multiply it here by 3, this 3, because we're multiplying our 43 by 23. So first let's multiply by 3. So that means basically creating 3 copies, right, of the same that we had here, okay? Okay, so we need 3 copies of that, right? Okay, so we multiplied by 3. So again, if I were to mark what happened, so I started with 43. I'm gonna highlight my kind of original number, right? 43, the first number, it was this. But multiplying it by 3, that meant creating 3 copies of it. So this corner here stands for 3 times 3. Anyway, we're in base 5. I'm not gonna write it, but remember that's all in base 5. This one here, we multiply by 40, so that's 3 times 40 in base 5. Okay, so we created 3 copies of longs and 3 copies of units. Okay, so now let's do let's multiply by 20. Okay, and let's first think, what would that mean if I wanted to multiply by just 1 0 in base 5. Remember when we multiplied by 1 0 in base 10, so by 10, right? That meant that each long became a flat, each unit became a long, and so on. So they basically were grouped, right, into the kind of higher dimension. But what about if it's here in a different base? Well, remember, 1 0 in base 5, that means 1 long, 0 units. So that means really 5 in our base, right? So if that means 5, then multiplying by 1 0 in base 5, meaning creating 5 copies of my longs. But remember, whenever in base 5, whenever I have a group of 5s, right, they jump into the higher dimension. So basically, multiplying by 1 0 longs will create a flat. Okay, so each long multiplied by 1 0 in base 5, same as in base 10, will create a flat, because again in base 5, 1 0 stands for 5, but 5 copies of longs will produce the flat, right, in this base. But now I'm supposed to multiply not by 105, but we're multiplying by 205. So we're basically multiplying twice by 105. So we have to do the same again. So twice we're getting those sets of flats. Okay, those are flats 5 by 5 again. Okay, so this was 20 times 40 in base 5. And here the same thing, when you multiply a unit by 10 in base 5, that will give you a long. But you want to multiply it by 2 zeros, so instead of one long, it will create two longs. Each unit will create two longs, right? So again, I'm looking at my, so this would be 20 in base 5 times 3 in base 5. So if you look at this highlighted original number 43 in base 5, each of this unit, when I multiplied by 10 in base 5, became a long. But since I'm multiplying by 20 in base 5, I have to make two copies of longs, right? So this is it. And now what number this one gives me based on this concrete model? What can I say is the solution of this 43 in base 5 times 23 in base 5? Well, we need to group. Whenever I have 5 units, that will become a long. 5 longs will give me a block, and so on. So what I see is that this will give me a long, right? So now how many longs I have? Now I have, I'm going to write it down. We have, so here, I'm going to write everything I have. We have 8 flats. Now, how many longs? We have 1, 2, 3 by 4. So this is 12 longs here. This is plus 6, so that's 18 longs. And this is one long we created from those units, right? So now we have 19 longs and 4 units. But from there, remember, whenever you have 5 longs, they will become flats. Okay, so how many 5 longs I have? This can be written as 19 as 3 sets of 5, right? So this will create 3 times 5, right? Plus 4. So this will create 3 flats. So now we have 8 flat. Maybe I'm going to write 8 plus 3, so 11 flats, 4 longs, and 4 units. Again, because 19 longs we had, I again have to group by 5, which would give me 3 flats. And you can also mark it on the picture. This is long, and now this will be that would be my flat. This would be my flat. And I would have maybe one more group of 5. This would be my flat. So I noticed that those gave me those extra 3 flats. And then I'm left with 1 long, 2 longs, 3, and 4, right? As I wrote here. But now what happens with 11 flats? Well, again, I group by 5. So 11 is, that's 2 times 5 plus 1. So that's going to give me 2 blocks. Because whenever I get 5 flats, it forms a block, right? So that's going to give me 2 blocks. And 1 flat, because I had 11. So 1 flat will remain. 4 longs and 4 units. So some of you could draw it again. So if you were to really truly illustrate it on the drawing, then you would have to, everything I wrote here, you would have to draw. So from this drawing, you would create 19 longs, right? Then you would show how 19 longs form 3 flats, right? And so on. Okay, so I'm not going to draw, it's going to take me too much time, but I hope you see the idea, right? Every time you have 5 flats, that they will create blocks and so on. And now I can write that 4, 3 times 2, 3 in base 5 should be equal to 2, 1, 4, 4 in base 5. Basically, 2 blocks, 1 flat, 4 longs, and 4 units. Okay, so that's called concrete model. So you're using concrete model to compute the multiplication. Okay, so let's look at the next example. We're going to compute 1, 1, 0 in base 2 times 1, 1 in base 2. I'm going to use standard algorithm here. So I have 1, 1, 0 in base 2. I want to multiply by 1, 1 in base 2. So first we multiply by a unit, right? So 1 times 0 is 0. 1 times 1 is 1. 1 times 1 is 1. Then we multiply by longs, right? So to indicate we multiply it really not by 1 but by 10, we're going to move one position over here. So 1 times 0 will be 0. 1 times 1 will be 1. And 1 times 1 will be 1. Okay? Because really, so what happens here, now we're adding 0, right? 1. 1 plus 1 is 2, but we're in the base 2, so whenever we have groupings of 2, we record how many units we have. So 2 means 0 units, and 1, 2. So 1 is carried over. So you always record here on the bottom number of units and how many 2's you have, or how many, depending on what base you have, you carry over that. So I have 1, 2, 0 units. And then 1 plus 1 is again 2. So that will give me 0 units and 1 long. So 1, 2. And then this, okay? So that's in the base 2. So that's the solution. And let's look at part B. Use the distributive property of multiplication over addition to explain why multiplication of a natural number in base 2 by 1, 0 in base 2 results in annexation of 0 to the number. So, okay, so we kind of had that in the concrete model when we did above in base 5, when I multiply by 1, 0 in base 5. I explained that 1, 0 in the base 5 really stands for 5. So when in concrete model I create 5 copies, then longs become flats becomes blocks, right? Because 5 copies of something, becomes the higher dimension. Okay, but in general, why is it that in any base, not necessarily 2, but in any base, multiplying by 1, 0 in any base will result in annexation of 0 to the number. Okay, let's kind of explain that. So in general, consider the number ABC in base 2. Let's say 3-digit number. So that will be A times 2 squared plus B times 2 plus C. We would have A flats, B longs, and C units, right? And let's multiply that number. Of course, here let me just mention that A and B, C are either 0 or 1, because in base 2, the digits that we can use is 0 up to 1, right? So then if you were to multiply that number in base 2 times 1, 0 in base 2, then if I translate it into our base, 1, 0 in base 2 is again 2, right? Because that's 1, 2, 0 units. Then what happened? This multiplication by 2 has to be distributed. So that will be A times 2 cubed plus B times 2 squared plus C times 2. And so now A denotes number of blocks, not flats. So you have A blocks, B flats, C longs, and 0 units. Okay. So notice what I just showed, that in general, if you multiply by 1, 0 in base 2, it just adds the 0 at the end the same way happens in base 10. Okay, So multiplying by 1, 0 in any base actually produces 0 at the end. That's why in the standard algorithm it works the same way, that here I can leave a room, or I can think, because it's really 0 in that place, because I was multiplying by 1, but right, this 1 here in purple, but in fact I was multiplying by 10, but the standard algorithm, we usually don't put the 0 because we know it's not going to play a role in the addition. We just move one as the second number 1 spot to the left, right? So that's kind of is justified. And use part B to explain why multiplication in base 2 by 100 in base 2, so by 100 in base 2, results in annexation of 2 zeros. Same we have in base 10. Okay, so I'm going to use the same example. So let's say I have the number ABC in base 2, but now I multiply by 100, not 10. Well, so I can do what I did previously, or I can just use the fact that now I show that, or maybe let's write the same way so we can see it more clearly. So now a times 2, we have a times 2 squared plus b times 2 plus c. We multiply by 100. 100 it stands for 2 squared, right? Because that's one flat, 2 by 2, 0 longs and 0 units. So now that's a times, now distributed. But multiplying by 2 squared means that 2 squared will become 2 to the power 4, because combined I'm going to have 4 factors of 2. This will give me 2 cubed, and this will give me 2 squared. So now what it means is that I have 0 longs and 0 units, right? But C flats, B blocks, and this one in dimension 4, I have no concrete model for that. But I have 0 units, 0 longs, C flats, B blocks, and A 2 to the power 4. So notice that it did result in annexation of 2 zeros. Another way that I originally wanted to start with is to say, okay, if you were using part B, because we haven't quite used here part B, but part B allowed us to say that, okay, 100 is 10 by 10, because by part B, 10 times 10, remember, is 100, because part B says whenever you multiply by 10, it's just annexes 0 at the end, right? And now multiplication is associative, so you can now multiply by 10 this number first, which again by part B, it just means annexing 0 at the end. But then you have one more multiplication by 10, so you will have to add another 0 at the end. And of course that would mean, it means adding 2 zeros. So notice it's the same, it would be the same in any other base other than 2. And it's the same in our base we're used to working with, that multiplying by 10 annexes 1 0 at the end, multiplying by 100 annexes 2 zeros, and so on. So we have the same. And use the distributive property of multiplication over addition, right, to compute this. So basically they want us to now use the knowledge we have that multiplying by 10 annexes 0 to perform this multiplication. But in order to do that, right, we're gonna do the following. Okay, so I'm gonna write 11 as 10 plus 1, and then this multiplication will be distributed. Okay, so multiplying by 10, we said just annexes 0 at the end, and multiplying by 1 in any base doesn't change the number. Okay, and now when you add it together, right, you're gonna get we're gonna get the same we had over there, meaning you're gonna have 0 units, 1 long. I'm gonna start from the back, 0 units, right? Then 1 long is just there, but now you have 1 flat and 1 flat. That creates 2 flats, and 2 flats will become 1 block, so you really have 0 flats because those 2 flats became 1 block. But now you have 2 blocks, right, with that block that's there. So now you have 0 blocks because the 2 blocks will create grouping of 2 to the power 4, which again we cannot use concrete model for the dimension higher than 3. But that's how you would add. Okay, so let's practice just using different bases, see, have fun with it a little bit. So let's use lattice multiplication to compute this. So lattice multiplication, I like it. I think it's pretty useful. Sometimes make life easier. We're in base 5, right? So remember, I'm sorry, we were supposed to do lattice. Okay, so lattice multiplication means that I create this grid, right? On top, I put the 4, 2, 3. And here I will put 23. So maybe here somewhere in the middle. 4, 2, 3, and we're in base 5. And here is 2, 3, and again we're in base 5. So I'm multiplying, and each field here is divided by 2 because I always multiply here will in each here square. On top I will denote how many 5s I have. On the bottom how many units I have. So how many longs and how many units. So 2 times 4, that gives me 8. 8 is 1 long and 3 units. 1 5 and 3 units. 2 times 2 is 4. So 0 longs, just 4 units. 2 times 3 is 6. 6 is 1 long, 1 unit, right? 6 is 1 5 and 1 unit. 3 times 4 is 12. 12 gives me 2 longs and 2 units because 12 is 2 times 5, right, plus 2. So basically 2 5s and 2 units. 3 times 2 is 6, that's 1 1, 1 long, 1 unit, 1 5, 1 unit. 3 times 3 is 9, 9 is 1 5 and 4 units, okay? And now you start from the right side. This is on its own, so it's being rewritten. And the rest along the diagonal you're going to add, right? So this, along this diagonal you're going to add. But again, if it exceeds 5, you just record number of units and longs are being carried over. So that doesn't exceed 5, so that's just 3. Then you add those. This will be combine 8. So you record number of units. 8 will give me 3 units because 1 5 I set aside and that's going to be carried over here. I recorded that in green. So now again you add those. That's 6, but you record number of units, right? So that's 1, and I forgot I was supposed to put this number here. So I can here add. So that's 6 is 1 unit and 1 long, right? So 1 is carried over. So always record number of units, and number of longs or 5s are being carried over, and this is just 2, right? So now if we read from this, we read from the top here and we just go down, right? So the result is 2 1 3 3 4 in base 5. Okay. Let's do in base 12. Remember, E stands for 11, T stands for 12. So now I'm going to do it correctly. So we create a grid. The top number will be 3 by 3. The side number will be 1 9. So E, T1, we will in base 12. And here's 1 9. Again, each square is split. and I do multiplication. And again, whenever I exceed 12, I'm going to record how many 12s I have and how many units, right? So let's start with which one? Let's do 1 times 1, that's 0, 1. 10 times 1, right? That's 10. 1 times 11, that's just 11. So we haven't exceeded here 12. That's why on top is all zeros, right? Now let's multiply by 9. 1 times 9 is 9. Again, we haven't exceeded 12. Now this is, remember, T stands for 10. 10 times 9, that's going to be 90. And how many 12s we have in 90? So 90 is 7 times 12, because that's what, 84 plus 6, right? So I have 6 units, 7 longs. So 7, 6 you record. Number of 12s and numbers of units, right? Because again, 90 would be 7, 6 in base 12. Okay, and 9 times E, so E is 11. 9 times 11 is 99. So that's, I think, 8 times 12 would be 96 and 3 units. So that's 8, 3 in base 12. And now I add along the sorts of this diagonal. But 9 is being rewritten. Then that becomes 7. If I don't exceed 12, then I just, nothing to be carried over. Now this is 10 plus 7 plus 3, so that's really 20, and 20 will fit, 20 will be what? 112 and 8 units. So I record number of units, right? And 112, so that 1 carries over. So now in the next diagonal, I have 11 plus 8, that's 19, plus 1, that's 20 again. 20, as we wrote before, is 8 units, 1 long, 1 12. And then you add the last diagonal with this 1 carried over will give you 1. So now you read, right, going this way. So that produced 1, 8, 8, 7, 9 in base 12. Okay, so let's do division, guys. Divisions are the most tricky, and I'm going to use this a repeated subtraction model, and I'm going to be just fitting just 1 or 10 times given number. I'm going to explain what I mean, because dividing in different bases is very tricky. But remember that this expanded algorithm, where we use the repeated kind of division, right, model, it works this way that I can first decide how many 43s I want to fit in the number, right? It doesn't have to be the best choice at first, but I will keep subtracting and then fitting 43 again. So I'm gonna start with fitting 10 times 43, because what do I mean? No, I know that that's gonna give me 430 in base 5, multiplying by 10, right? Annex is 0. So I need to subtract that. So I have 10, right? I'm fitting 10 43s. So which then means I need to subtract 430. So 1 minus 0 is 1. Now 1 minus 3, not enough, right? Longs. So I have to borrow the long from this. So that's going to give me now 2 flats. And now I have 2 longs, right? I'm in base, what I'm talking about. I'm in base 6, right? So 1 flat will create 5 longs. So now I have 6 longs. 6 minus 3 is 3. But now I have only 2 flats, not enough to subtract 4. So I borrow from blocks. Now I have one block, but one block will create 5 flats. With the 2 I had, now I'm gonna have 7 flats, right? So that's 7 minus 4 will give me 3. And then I'm left with one block I had, right? So now let's fit again 10 43s in it. I want to divide by 43, so I want to see how many 43s I can fit. 10 times 43, I know it's 430, right? So let's fit in that many 43s and subtract that and see what's still left and how many 43s I can fit again. Okay, so then that's 1, 0. I borrow from a block, which one block will create 5 flats. So now we'll have a total of 8 flats minus 4. That's going to give me 4. Okay, I clearly know I won't be able to fit 10 copies of 43. So let's start with, I don't know, let's start with... how much we can fit. Maybe let's go with 2 copies of 43. What's 2 times 43? And base 5, right? 2 times 3 is 6, but 6 is 1 unit, 1, 5. 2 times 4 is 8, plus 1 is 9, and 9 is 1, 5, and 4 units, right? So that's 141. So now I have to subtract that and see what's still left, okay? So that's 0. I borrow from a block, which creates 5, I borrow from a flat, which creates 5 longs. And so I have this. So it seems I can fit 2 times 43 again, because I know it's already 141. So let's see, can I fit that still? So I borrow from, let's go from a block. So I have one block will create 5, I have 2 flats. It will create 5 longs. With the 1 long I already have, I'm gonna have 6 longs. But then I'm gonna use 1 long to help here with my units. So 1 long will create 5 units. So 5 minus 1 will give me 4. 5 minus 4 will give me 1. 1 minus 1 will be 0. And I can't fit in this 43 anymore. So that's my remainder. So now what's the quotient? So quotient now is how many times totally I fit 43 in it. 24, right? Times 43, okay? So that means that the quotient is 24. Again, that's how many times I fit 43 in the number. And then the remainder is 1/4. So remember, this repeated subtraction kind of expanded division algorithm allows you to not know exactly what's the biggest number of times you can fit 43 in the number. You just start with whatever you know. Start with 10 is the easiest, or 1 time. Subtract that, see what's left, and again fit again as many as you think you might be able to fit. Okay, but let's look at the standard algorithm for that, how that would look on the standard algorithm. So now that I know that I could fit 2 times, right? That means that in this 2 times 43, by the way, I calculated it here, is 141. So I can fit 2 times, right? So basically 43 is 4 longs and 3 units, right? So for sure I'm not going to be able to fit it in number 2 itself, nor number 23, 2 longs, 3 units. I need more. I need 2 flats, 3 longs, and 1 unit. So I know it's going to fit twice because I kind of have the answer. Its quotient should be 24. 2 times 43, we multiplied, that was 141. So now you need to subtract it. So then you borrow from this, which will create, you're in base 5. So that will create 5 longs. So you have total of 8 longs. So that's going to give you this. You carry over that one here. And now, you know, it's going to fit 4 times. 4 times 43. We can perform that. And base 5, now I have to do, right? So 4 times 3 is 12. 2 units, 2 5s. 4 times 4 is 16, plus 2 is 18. 18 will be 3 5s, right? Because that's 15. And 3 units, so that's 332. So now subtract that. So borrow from your here flat, which will create 5 longs, but borrow 1 long because that will create 5 units. So you're gonna have a total of 6 units with the 1 unit you already have. So now we can perform this. 6 minus 2 is 4. 4 minus 3 is 1, and 3 minus 3 is 0. And that's going to be your remainder because you cannot fit 4 3 in that anymore. And notice I didn't have to do it second time. I just wanted to show you how that would play out if you use the standard algorithm. Let's do part B. Part B was, actually let's skip part B. I'm probably not going to give you the complicated division like that. Let's perform each of this operation. Let's start with multiplication. And again, guys, you can use maybe this lattice algorithm for multiplying if that's what is more convenient for you. Or you can use standard. So I'm going to use standard, but again, feel free to use lattice. So 4, 2 in base 5, I'm going to multiply by 3 in base 5. So 3 times 2 is 6. 6 gives me 1 unit, 1 5. Remember, on the bottom is number of units. What you carry over is number of 5s. 3 times 4 is 12, plus that 1 is 13. 13 gives me 3 units, 2 5s, okay? And you have it. Okay. Now 22 in base 5 divided by 4. And you divide by 4, okay? All right, that one, guys, it's small enough number, so I can probably visualize how many times I can fit 4 in it, because 22 means 2 longs, 2 units, right? The longs are, 2 longs give me 10, right? 2 longs give me 10 units, plus 2, I have 12 units. So it seems like I can fit 4 3 times. Let's check. 4 times 3, it gives me 12. And 12 is 2 units and 2 5s. So that's it, right? So basically what I did, I visualized that you can even use concrete model. If you have 2 longs, right? Each has 5 units. That's small enough number that we can just visualize it, and 2 units. You want to divide by 5, so you split, you create 5, right, units, and here you have 2 more, right? So then you group by 4 because you divide by 4, so you see you're gonna have 3 sets of 4, right? So you have it. So the quotient is 3, remainder is 0, basically 4 fits fully into 22. Let's do the multiplication. 3 2 by 4 2. Again, try to do it maybe using a lattice algorithm. I'm not imposing any particular algorithm here. I'm going to use standard. 2 times 2 is 4. 2 times 3 is 6, but I'm in base 5. So 6 is 1 above 5. And gives me 1 5, 1 unit. First unit, then number of 5s. Then I multiply by 4 and I start with 1 over here. So 4 times 2 is 8. 8 will give me 3 above 5, right? And 1 5. 4 times 3 is 12, plus that 1 is 13. 13 will give me 3 above 5 and 2 5s, right? 13 is 2 5s and 3 extras, right? 3 units. So then I have to add, that's 4, 4, 4, 2, because whenever I don't exceed 5, it just stays as it is. So I have, okay, let's do this one. That one is, division is always complicated. So remember what I will do, I will start with 10 times 23. I'm trying to fit 23 in the number. So let's start with 10 times, right? Because I know 10 times 23 is 230. It's just annexing 0, right? So let's subtract. So 3 minus 0, units to units, so that's 3. 1, not enough to subtract 3, so I borrow from this. This will create, one flat will create 5 longs with the 1 long that I already have. That's going to be 6 longs. So that when I subtract now 3, it's going to be 3 and nothing left, right? And of course, so let 0, and of course that 1 here carries over, right? Because the number was bigger. Okay, so then now let's fit again 10 times 3, because that's just 230. Maybe I could have gone with bigger number to begin with, but remember I'm not sure how many times. I start with always just 10 times. So 3 minus 0 is 3. 3 minus 3 is 0. 0 minus 2, I don't have it. I borrow from this. That's going to give me 5, right? 5 minus 2 is 3. Alright, so it seems like I can again fit 10 times 23. Because it seems like 230 I can fit again in that. So now let's take away 230 and let's see what's left now. 3 minus 0 is 3. But 0 is, I cannot subtract from 0, 3. So I borrow from this, which create 5, right? Longs. 5 minus 3 is 2. 2 minus 2 is 0. So I have 2, 3 base 5. Which now I can see I can fit 1 times 2, 3. Because 1 times in any base is just that number. And when I take it, I have 0 remainder. So combine how many times I fit 23? 31 times. 31 times 23, right? Has been fitted in my number, which means that that's the solution. So quotient of this division is 31 and the remainder is 0, which means that this is just 31, the solution of this division. Okay, wasn't too bad, although division is always intimidating. Okay. Let's do this multiplication. Oh, that should be easy because multiplying basically by ones shouldn't be a problem. So first 1 times 1 is 1, 1 times 0, and 1 times 1. So I'm multiplying by this one. Then I'm going to multiply by 0, right? So I need to kind of move one place over, and everything multiplied by 0 would create 3 zeros. And then I'm going to multiply by this one. So then again, moving 1 over is going to give me 1, 0, 1. So now I'm going to add. That's 1, that's 0. 1 plus 1 is 2, which means 0 units, 1, 2. 1 is carried over. I'm going to mark it in green. Then that's 1 and 1. Division, guys. Okay, so again, division. Here 1 0 0 1 in base 2. Whenever I'm still in the concrete model, I try to visualize it, because in base 2 it's not a big kind of visualization. This is like a block, right? This would be flat, this will be long, and this will be unit. So basically I have one block, right? One block, 2 by 2, and 1 unit, okay? And I want to fit 1 1, right? 1 1, it's 1 long and 1 unit, so that's really 3, okay, in our base. And this is really, block is like 2 by 2 by 2, so that's 8. This is really 9, so I'm dividing by 9 divided by 3, I know it's 3. So basically what I really did, I converted to our bases, and I know that it's gonna be 3 or 1 1 in base 2. Okay, or let's so basically one approach would be, especially if the base is small and I can quickly visualize what it is, that's 9, and 1 1, that was 1 long, 1 unit, so 1 1 was 3, so that's really 9 divided by 3, which is 3, which if we were to go back again to the base 2, that's 1 1, right? So maybe sometimes converting to our base is easier, not always. But what if we wanted to do the standard algorithm? Let's try to use the standard algorithm. Let's try to divide. So what I'm thinking is that's like 1 long and 1 unit. I won't fit it in 1. I won't fit it in 1 long 0 units, but I should be able to fit it in one block, right? Because one block will have one flat, 1 0 0 is 1 flat, right? Should fit it once, right? Because one flat, in 1 flat, I want to fit 1 long and 1 unit. I won't will be able to fit it more than 1 long, right? And 1 unit, I can only fit once in 1 block, 1 flat. Okay, so I put 1. So 1 times 1 1 is 1 1, and then I have to subtract it. But again, that flat will give me two longs, but I only will leave 1 long, and one of the longs I will carry over to give me 2 units, right? Okay, so that's gonna be 1, and that's it, right? So again, this one flat created 2 longs. I left 1 long, and the other long created 2 units. And then you were able to perform the subtraction, ended up being 1. You carried that 1 over, and then you see that how many times you can fit 1 1 into 1 1? Once, and the remainder is 0, right? So that would be a standard algorithm for that. Or we could have just converted to our base and get the answer. So we have this, okay, and let's do this multiplication. Just to mix it up, I'm going to use the lattice now, because I feel like some of you might find it easier. So 4 3 in base 6 multiplied by 2 3 in base 6. And so we're recording number of, remember, number of units on the bottom, and on top number of 6s. So let's do 2 times 3 is 6. So 6 is 1 0, 1 6, 0 units. 2 times 4 is 8, which gives me 1 6, 2 units. Then 3 times 3 is 9, 1 6, 3 units. 3 times 4 is 12, 2 6s, 0 units. And then along the diagonal, you would add 3 This diagonal will give you 1. This one will give you 5. And this one will give you 1. So the answer would be 1, 5, right? Reading from this way, that way. So that's 1, 5, 1, 3. Right? If you use the standard algorithm for the same, then 3 times 3 would be 9. You record number of units and how many 6s you have. 3 times 4 is 12, plus 1 is 13. 13 is 2 6s and 1 unit, right? And then you multiply by 2. 2 times 3 is 6. That's 0 units, 1 6. 2 times 4 is 8, plus 1 is 9, and 9 is 1 6, 3 units. And then you add it, and you get the same answer, right, as before, okay? Okay, let's look at 1, 4, 3, 5 divided by 3. I'm going to try to use a standard algorithm. I know I won't fit 3 into 1, but what about into 1, 4? In base 5, that's 1 long, which is 5 units, and 4 units, so that's 9, really. So I should be able to fit 3 times. So then let's go back. 3 times 3 is 9, and 9 is 1, 5, 4 units. So actually when you subtract it, nothing will be left, right? So I carry over this 3, and now 3 divided by 3 is 1. 1 times 3 is 3. You subtract, remainder is 0. So that solution is 3, 1 in base 5. Okay, division by 10, since multiplication by 10 annexes 0, division by 10 gets rid of the 0, right? So that's just basically this. So that's nothing to think there about. Let's use this one. Okay, so now let's multiply this. Again, you can use here lattice multiplication. I'm going to use standard multiplication, and base 2 is pretty easy because you only multiply by 1 or 0, right? Just adding can get tricky. So let's see what's going to happen here. All right, so first multiply by that. 1 times 0 is 0. Then 1, 1, 0, 1. Then you multiply by another 1, but with one place over, right? So 1 times 0 is 0. 1 times 1 is 1, right? And basically, you're going to multiplying by 1 will just recreate the same number you had, right, above. And then you multiply by that 1. So again, we'll just copy that number you had on top, but with 1 place over, right? Okay, and now we have to add. So this 0 is just carries over, right? Now 1 plus 0 is 1. Now 1 plus 1 is 2. We're in this base 2, so 2 is 0 units, 1, 2. Then that's 1 plus 1 plus 1. That is, and I'm going to put in green what we carried over. That's 3, and 3 is 1 unit, 1, 2. Okay, so that's again 3, 1 unit, 1, 2. 1 plus 1 is 2, 0 units, 1, 2. And 1 plus 1 is 2, 0 units, 1, 2. So 1 goes down. So that's the solution of this multiplication. I'm going to rewrite it here. Okay, guys, if you know the how to divide things, regardless of the base, you should be fine. Let's do this, and I know we're so used to an hour base 10, so switching the bases, it's a good exercise to kind of understand those algorithms even better. So E stands for 11. 2 times 11 will be what? 2 times 11 is 22. And 22 fits how many times 12? That's 112 and 110, but we denote 10 by T, right? So so that stands for number of units. This how many 12s you have. So basically this is 1T in base 12. So I put T and 1 carries over. Okay. Then 2 times 3 is 6 plus that 1 gives me 7. And 2 times T, so 2 times 10 is 20. And 20 will be 112 plus 8. So that will be 8. So I put 8, right? And 1 carries over. So it goes down. Okay. Then I'm going to multiply by 7, right? So let me scratch that off so I'm not confusing this. 7 times E, 7 times 11 is 77. 77 is how many 12s I can fit. 6 times 12 would be 72, right? So that will be 6, 5 in base 12. 6 12s and 5 units. So I record number of units, right? And number of 12s I record here. Now 7 times 3 is 21, plus that 6 is 27, and 27 would be 2 times 12 because that's 24, and 3 units, so that would be 2, 3 in base 12. I always put here number of units, so 3, and number of longs, 2, carries over. And then 7 times T, so 7 times 10 is 70, plus that 2 will give me 72. And 72, I'm going to write it down here, 72 will be, I think, 6 times 12, right? That's exactly 72, so that's going to be 60 in base 12. So 0 units, okay? And 6 12s, so that carries over is here, 6. Now you have to add, T gets down. 7 plus 5 is 12. 0 unit, 112. 8 plus 1 plus 3, that's 12, right? Against 0 unit, 112. Then 1 plus 1, that's going to give me, again, this is the numbers I carried over. That's just 2 and 6. So that's my final answer. Okay. Okay, and I'm gonna just skip this division. It's too difficult. I'm not gonna. You can check how I solved it if you want, but that's it for this week.